Before we get into this, take a minute to reflect. Joke works better in a real class. Got some mirrors here. You can see a bunch of different cool looking reflections. Give me just a second. Got some curved mirrors. Let me get this one out of the way. We've got this weird looking thing called a retroreflector. This is like the reflectors you have on your bicycle. You can see a bunch of flat mirrors with angles. Got this other mirror here. Hold on, I don't want to drop this. Got a curved mirror. It's kind of cool. You can see a bunch of different reflections. All right, let's get these out of the way. And we want to understand reflections, and later on we want to understand image formation. But first, let's learn the basics, the terms, and how we can use them with flat mirrors, and then we'll take it from there. Let me rotate this for just a second so I can see. All right. We're going to talk about light reflecting off of mirrors. So let's just imagine we have a light ray here. I'm going to use lasers in a minute, more on that. And so let's say this is a light ray. Sometimes we'll call it the incident light ray, the light ray that's coming in. This is going to be mirror 1 down here. And we'll say the light ray comes in at some angle of incidence. It's usually theta subscript I. We might use numbers, more on this practical example in a minute. There's the angle of the light that's reflected. We call that theta reflected. Sometimes it might be 2, 3, or 4, and more on in a practical example in a minute. These angles are always measured relative to the normal to the surface. Normal, in this case, being the mathematics perpendicular to the surface. And so for both flat and curved surfaces, we're going to assume angle of incidence equals angle of reflection. Theta I equals theta R. Let's look at how this plays out in a practical example. I'm going to try to draw this perpendicular as best I can. I'll get out of the way in a minute. So this is the normal. I'll call that normal 1. Can you read that? Kind of. All right. This we could call theta 1 incident. Right? That's this angle right here. Now I'm going to try to draw this as best I can so that the angle of incidence, that's approximately equal to the angle of reflection for mirror number 1. So this is theta 1 incident, this is theta 1 reflected, and notice this angle is supposed to be equal to that angle. Here's mirror 2. I'll call this normal number 2. Sorry, it gets kind of crowded in here. Notice big pictures might help when you're doing optics. Don't try to squeeze everything in really tiny. A half page or more might be nice. Going to try to make this angle look equal. All right, this is sometimes called the outgoing ray. So we've got the incident ray and the outgoing ray. And so here I might call this one theta 2 incident. And this could be theta 2 reflected. Make sure that shows up. Close enough. Furthermore, we can actually extend some of these rays. Like, for example, this is the incident light ray, the incoming ray. And I'm going to what's called back extend this reflection. This ray is going out this way, but I'm going to back extend it best I can. And so we could call this angle here maybe lowercase delta. So we're oftentimes going to use the letters alpha, beta, gamma, and delta to describe angles in these problems. So for example, maybe I want to give a name to this angle right here. Maybe I could call this angle beta. Again, you can see the need to draw big pictures here as you start to label things and try and do geometry on these. We're going to definitely need some, and I guess strictly speaking, maybe I'll do these with 3, right? Each angle should have a different number. It gets pretty crazy in here. Right, because this angle is not necessarily the same as that angle, not necessarily the same as this or that. But a classic problem is to try and figure out the deviation angle delta between the outgoing ray and the incoming ray if you know theta incident and beta. We could maybe do that problem later. And in fact, I have this example set up with some lasers. I'm going to mention some lasers safely briefly. You can read here. This most important things are right here. Don't do this at home. I can do this because I was trained. There's also nobody in here. But if you're doing, we don't want to be blind. All right. So screwing around with lasers, even laser pointers, you could be blind. Let's not take that chance. Keep your eye out of the laser beam. Don't do this at home. In here, no one is in here but me. And so you may see some, I've used some tape to secure the lasers. That in general is a terrible idea because tape can go bad and get knocked loose. But because I'm the only one in this room and because I have training, I feel safe. One thing you want to watch out for example, is watches, right? If you have a watch and you put it in the laser beam and there's a reflection off the watch into your eye, you could go blind. It's that simple. So in short, don't try this at home. I have some training, so I feel safe. But let's go take a look at an example and see why doing some lasers in class can be a little bit tricky at first. All right. So this is that same exact problem that you saw on the board, right? We see the laser beam. It's actually on right now, and I know where the beam path is, so I feel safe. You might not be able to see it. I'm going to try and help out here. There we go. And actually, let me zoom in a little bit on this so you can see it better. Zoom in. And I'm going to tilt it just a little bit there. All right. Oops. Let's tilt that back up. All right. There we go. I can see it now. And I need to rotate my screen so I can see from the other side of the room. All right, let's get to it. Now, I don't know if you can tell that that laser beam is on or not, but what I've done is I've got this white card I can use. That was my old roommate, by the way. He paid to have this photo taken. You can use the back of the card to trace out the path that the beam travels and see it. I'm being very careful to keep this is generally speaking a terrible design because the laser is going up in the air. So we really want to avoid getting your eye in this plane. This is the plane of the beam at this time. And notice it's going right up towards my eye, but because no one else is in here and I have safety training, I feel confident that I can do this without going blind. You might be wondering what's going on over here. What is this black thing? This is called a beam expander. Hopefully you can see this point on the screen here. You'll see a tiny little laser dot. It goes in here, there's some optics, and it comes out as a big laser dot. That actually increases the safety because there's less intensity, power per unit area. By increasing the area, I'm less likely to go blind, which is a good thing. Okay. But so hopefully you can see this path is taking, the path of the laser beam is approximately what we saw in the sketch on the board. Why can't you just see the laser beam all the time? Well, this is air here. There's not a lot of particles in the air. I could try to do that with some chalk dust, and it doesn't work very well on camera. I've tried this in class, you could see this, but the camera is just not sensitive enough to see this. I could take some chalk dust, and I could see the beam quite well now, but you probably can't on camera. It's there, but you need some kind of particle to reflect the laser light into your eye for you to see it. Because there's not a ton of particles in the air, you're not going to see the laser beam unless you use something like a white card to reveal the path. You could say, why don't you use a fog machine? It sets off the fire alarms in this building, so I can't do that. All right. I think that's probably enough said on this. But one thing you could see is if you change the angle, let's just try that a little bit. Oh, I know there's one other thing I did want to say. 2 more, I guess. You could change the path of the beam by changing the angle, right? Or I could make this a little bit lower. Let's do that way. Right? And so depending on the angle that you input this, you're going to affect the output path. So that's kind of interesting. Also, I want to take this beam expander out, being careful not to get the beam in my eye. I'm going to show you this. I don't know if you can see this very well, but there should be multiple spots of the laser coming off. Why are we seeing a single laser beam over here, but multiple spots over here? It's because there are reflections from each surface, and I can show you another example in a minute to verify this. But the idea is the laser light comes in, some light reflects off the front surface of the glass. Then it hits the actual silvered surface, the back, and some of that light is then seen. Furthermore, there's light that bounces off the mirror, off the front, then off the front towards the back. And then again, so we see multiple reflections from the beam bouncing inside the plane of glass. And this happens when you have it at a slight angle. But if we drop this angle down, you probably won't see it as much. Probably see a little, maybe you can see it a little bit better actually. Where did it go? There it is. So, but actually we're seeing fewer bright reflections. We're seeing a couple, but you're always going to get a few reflections from each surface. So that's something in the real world that complicates these problems, right? We always talk about just one beam, but in the real world, there's often multiple beams. Let me show you one more example of that. Okay. And a technique. Let's go to object 4. Camera 4. Okay. Careful here. Give me a second. Okay. Put a weight back here. All right. So now I'm being careful to avoid getting hit with a laser beam. Maybe you could see this a little bit on the screen here. You might be wondering, wait, how come I could see this laser beam? This laser beam is actually aimed at the whiteboard, and the whiteboard is what's reflecting it to you, right? So it's actually a slightly angled beam, and it's spread out with a cylindrical lens, so it's whatever. The point being, you're seeing a reflection of some of the laser beam off of here. And I just want to point out, if I rotate this, this is just a piece of plastic. This is not a mirror, right? Just showing you, this is not a mirror. It's just a piece of plastic. And I'm going to hit the lights so you can see better. We'll discuss refraction later, but I want to focus your attention here. I hope you can see this beam coming up here. I'm trying to emphasize it with my finger. I'm just letting my finger reflect the light into your eye. Notice there's a reflection off the front surface. Okay. And if I had a slab, I'm going to try and grab a slab real quick. Just give me a second. Here it is. Going to get rid of this D-shaped lens. And we'll do math in a minute. But one of the things you could see there, maybe you could see it very faintly. Here's one reflection off the front surface. Here's another reflection, if I can get my finger on it, off the back surface. So we're seeing multiple reflections off each surface. Let me get a triangle in here. Okay. And so we could see there's different reflections off different surfaces. And you could see a strong reflection right here. Right? But you can see lots of different reflections happening. So it's important to always understand where your laser beam is going. And one of the issues we always face is at every surface, you're always going to get these reflections. I think that's enough said on that. I'm going to go ahead and stop the video.